Hello everyone. In continuation to our topic research methods, in this video we will understand how do we do a numeric analysis for a Latin square design with the help of an example. Here the question is, the production manager of a firm is keen in analyzing the actual hourly production volume of a product. He feels that operators A, B, C, and D, machines M1, M2, M3, M4, M5, and suppliers of raw materials S1, S2, S3, S4, S5 will affect the production volume of the product. Hence, he designed a Latin square design as shown in the table below, which is table 1. And then the corresponding observations, whatever he collected about the production volume, are shown in the table 2. First, table 1, experimental combinations in Latin square design. We have here rows machines, columns suppliers, and inside we have the operators arranged like A, B, C, D, E. Then it starts with B, C, D, E, E, and A. Then it starts with C. Likewise, the design is made. Then the production volume is captured after doing the experiment in this fashion. So the production manager got this values, means if the operator A operates on machine 1 and the material is from supplier 1, how much is the production volume? Same way, if operator A operates machine 3 and the material is from supplier S4 raw material, then the production volume is 8. Like that, this entire data is captured. So we need to perform statistical analysis to test the following at a significance level of 0.05. Whether there is significant difference between operators in terms of production volume of the product. Second one, whether there is significant difference between machines in terms of production volume of the product. Third, whether there is a significant difference between suppliers in terms of production volume of the product. So now the model for this LSD will be Yijk, which is equal to mu plus Mi plus Sj plus Ok plus Eijk, where Yijk is the observation in the ith row, jth column for the kth treatment. Here row is representing machines, column is representing supplier, and the treatment is basically our operator. Mu is the overall mean. M suffix I is the effect of the ith block representing machine. What is the effect of the machine? Sj is the effect of jth block representing supplier. OK is the effect of kth treatment of the factor representing operator. E suffix ijk is the random error associated with ith row, that is machine, jth column, that is supplier, and kth treatment of the factor, which is the operator. Then what we did here in this table is, from this data, whatever is being collected, we just got the column totals and row totals. Means 12 plus 8 plus 9 plus 15 plus 18, we get this 62. Similarly, column, this one, let us see, 9 plus 13 plus 12 plus 13 plus 8, we get this 55. Then we are rearranging the hourly production of volume in LSD based on the operators, means operator A, B, C, D, E. So if I consider, like, for example, in the machine 1 and operator A, it is 12, we wrote here. Machine 1, operator B, where is that? Here it is 8, then 9, then 15, then 18. When you come to machine 2, operator A, it is 12, operator B is 14. So I rearranged it. And then operator C, it is 7. Operator D, it is 13. Operator E, it is 10. So after rearranging, we are adding the total based on the operator, 59, 47, 45, each column's total. Now, we will proceed with the first formulating the hypothesis. Let us say, first test will be related to operators. So here the null hypothesis will be mu, that is the population mean if operator 1 is operating, that will be the same as mu operator 2, that will be the same as mu operator 3, which is same as mu operator 4, that is same as mu operator 5. Then alternative hypothesis will be at least two of the above means are not the same or not equal. Now let us define clearly what is this mu. Mu O suffix k is population mean hourly production volume due to operator O suffix k. So here k takes the values 1, 2, 3, 4 and 5 because there are 5 operators. This is our first test which is based on the operators, or we can say treatments. Next, second test. Test 2, which will be based on machines. So here H0 will be mu suffix M1, mu suffix M2, mu suffix M3, mu suffix M4, mu suffix M5. Means there is no significant difference between the hourly production volume due to any of the machines. That is our null hypothesis. Alternative hypothesis will be similar to the above, means at least two of the above means are not equal. So here we will define where mu suffix mi is the population mean hourly production volume due to machine mi, where this I also takes values from 1, 2, 3, 4 up to 5 because there are 5 machines. Next, this is based on, you can say, rows. Machines are representing the rows. Then test 3. Test 3 is related to suppliers, which is columns. Here again, H0 mu suffix S1 will be the same as mu suffix S2. Means there is no significant difference between the hourly production volume due to any of the supplier, due to any of the 5 suppliers. H1 again will be similar to what we wrote earlier. At least two of the above means are not equal. Again, we will define what is mu S suffix j, which is population mean hourly production volume due to supplier jth supplier, where j ranging from 1, 2, 3, 4 up to 5. So this is the third test. So the very first step is to find out correction factor. Correction factor, which is briefly abbreviation is CF. CF is the grand total square divided by total number of observations. Here the grand total, let us see what it is. 284, total number of observations. Every row has got 5 observations. There are 5 rows, so totally 25 observations. So 284 square divided by 25. So if we calculate this, we will get CF, that is correction factor, as 3226.24. Now let us find out sum of squares of rows. That is, every row we will take the total, square the total. First row 62 square plus 56 square plus 48 square plus 69 square plus 49 square. Then it has to be divided by the 62 made out of 5 observations. Every total is made out of 5 observations. So everything has to be divided by 5. Then finally subtract it with the correction factor. Means this will be 62 square plus 56 the square plus 48 square plus 69 square plus 49 square. Every observation made out of 5, so we are dividing it by 5, minus the correction factor, which is 3226.24. If we calculate this, we will get 62.96 as the sum of squares of rows. Proceed to the next thing. Next one is sum of squares of columns. Every column's total will be squared and then summed up. Means 58 square plus 61 square plus 55 square plus 54 square plus 56 square. Every total is made out of 5 observations. So again, it will be divided by 5, subtracting with the correction factor. So your SSC will be 58 the square plus 61 square plus 55 square plus 54 square plus 56 square divided by every observation made out of 5, minusing with correction factor. Correction factor is 3226.24. If we calculate this, we will get 6.16. Right? Then next one. Sum of squares of treatments. We had already made the rearranged data for the treatments. Here the treatments are the operators. That means this column's total, operator, each operator's totals square, which means 59 square plus 47 square plus 45 square plus 67 square plus 66 square. Each of these total is again made out of 5 values, so you have to divide it by 5. Finally, subtract it with correction factor. So 59 square plus 47 square plus 45 square plus 67 square plus 66 square divided by 5, subtracting that with 3226, which is correction factor. So if we do that, we will get 85.76. Then we need to do this total sum of squares of total. That is what? Every observation in the original table needs to be squared. Means 12 square plus 8 square plus 9 square plus 15 square plus 18 square plus 14 square and so on. 10 square plus 8 square means all these observations needs to be squared and then subtracted with the correction factor. That means 12 square plus 8 square plus and so on. The last observation is 8 square in the full table. Means this entire data is of those 25 observations. Every observation is getting squared and subtracted with the correction factor. If we calculate this, whatever is inside the bracket, we will get 3498 minus correction factor is 3226.24. We will get 271.76. So we got all the sum of squares. Now we need to find out what is the sum of squares of error. That is sum of squares of total minus sum of squares of rows minus sum of squares of columns minus sum of squares of treatments. And that will be 271.76 minus sum of squares of rows is 62.96. 62.96 minus sum of squares of columns is 6.16 minus sum of squares of treatments is 85.76. If we subtract all this, we will get the sum of squares of error as 116.88. Now we are ready with all the data required for the preparation of ANOVA table. Now let us fill up that. Means first one, between rows, the degrees of freedom. How many rows? We saw already it is 5 rows. So our degrees of freedom will be 1 less, that is 5 minus 1, which is 4 degrees of freedom. Number of suppliers also 5 minus 1, 4 degrees of freedom. Number of treatments is also 4. I think just a moment. Can we be able to adjust? We see. Yeah, treatments also 5 minus 1, 4. Total 25 observations were there. 25 minus 1, we get 24. Means error will be the balancing figure. 4 3s are 12. 24 minus 12 here. 24 minus that 12, you get 12 degrees of freedom. Now sum of squares we calculated. For rows, it is 62.96. And for columns, it is 6.16. For treatments, it is 85.76. For error, it is 116.88. Total, it is 271.76. Now, mean sum of squares for the first one, it is 62.96 divided by the corresponding degrees of freedom. If you do that, you get 15.74. Then next one, 6.16 divided by 4, we get 1.54. Next one, 85.76 divided by 4, we get 21.44. Error, 116.88 divided by 12, we get 9.74. Now, F ratio, For rows, it will be this 15.74, whatever mean sum of squares we got in that corresponding row, divided by the error mean sum of squares, which means 9.74. If we do that, we get 1.616. Next one, columns, that is 1.54 divided by 9.74. If we do that, we get 0.158. Next one, 21.44 divided by 9.74, we get 2.201. Now, for this one, here the numerator degrees of freedom. I mean, numerator means this 15.74 degrees of freedom is 4. Denominator 9.74, that is degrees of freedom is 12. So 4, 12, we have to look for the table value. 4, 12 degrees of freedom. For 5% level of significance, the table value is 3.26. Now we may notice calculated value is lesser than table value. So inference will be, we accept H naught, means there is no significant difference between the production volume due to machines. That is the meaning of it. Next one, here again, the numerator degrees of freedom is 4. Denominator is again 12. So again, here it is 3.26. Again, here we will, since the calculated value is lesser than the table value, we accept null hypothesis. Here again, it is 4, 12. So it is again 3.26. So we accept, 2.201 is lesser than 3.26. So we accept H naught. So in all the tests, we are accepting H naught, which means that we don't find any significant difference in the production volume due to machines, due to suppliers, due to treatments. That is the conclusion or solution for this particular question.